Hi guys, so this is actually the first in a multi-part video series on parametric equations. In this video, we're going to look at really just the definition of parametric equations and how to visualize them graphically. It would be helpful if you have a calculator handy because I'll go through a couple of calculator steps as well as either the note packet that I provided or just a piece of paper that you could write this information down on. So first off, I'm going to start by posing a problem, which is that say a baseball is thrown into the air, and I have two functions that each measure one function measuring its horizontal distance and the second function measuring its vertical height, each as a function of time. So depending if I threw it 2 seconds after I've thrown this ball, it will have gone 80 feet horizontally, and then I could plug 2 seconds into this equation to find out exactly how high off the ground the ball would be. And I could plot each of those two graphs here. So for a given moment in time in seconds, I can see how far it's moved horizontally in feet, and similarly, what its height is for that given time as well. But what I would like to do is to eliminate this variable of time and just show the path that the ball took. So to visualize across time the path that this ball travels when it's thrown both horizontally and vertically. Okay, and to do that, that's where we're going to need some parametric equations, or equations defined in terms of a parameter, t, time. Okay, so here's how that's going to work. So I'm going to want to visualize both the horizontal and vertical heights or distances in terms of time. So we have two continuous functions on an interval. And if I notice the path of this ball, it looks like it travels from 0 to 4 seconds. So it looks like time is varying between 0 seconds and 4 seconds. So the ball stops traveling after 4 seconds. That's the limit on my time, where time is going to be my parameter here. And I'm going to define x to be my horizontal distance. Makes a little bit of sense. It's a horizontal variable. So I'm going to let x be the function f of t. I'm going to let y, my vertical distance to represent height, to be g of t. So both the x and the y coordinates are defined in terms of time, where time is this third variable we call the parameter. So t is the parameter. We say that this interval that it's traveling between 0 and 4 to be the parameter's interval. And then we're going to look at all the order pairs x, y are now these functions f of t and g of t. And those make up what we call the parametric curve, which is going to be the path of the ball. Okay, so let's actually go through and graph that. So I have all my values. So I'm going to look at what would happen if I try to graph the path of this ball as it was defined. So to start off, I'm going to write a set of equations for the x and y values and the interval. Now we've already talked about that. So each x coordinate is going to be 40t. That's coming from that horizontal distance. And y is this equation coming from that vertical distance. And again, t is varying between 0 and 4 seconds because at that point, the ball has hit the ground. It has a height of 0. Essentially, if we want to do this, I'm just going to plug in different values of the parameter, which fall on this interval, and see what I wind up with. So I'll probably start with 0, and then I'll maybe do 0, 1, 2, 3, and 4, and plug it in for each value for x and each value for y, and I'll get this table of values. You could see if you pick any one to see where these values come from. Like if I plugged in 2 times 40 would give me 80. If I plug in 2, negative 16 times 4 plus 48 times 2 plus 64 is going to give me 96. So those are each of my values, and I'm going to have to plot each of those values on this interval. So on this graph. So I'm going to have to scale it out. Now to get a sense of the scale, I could look at my individual graphs to see what values the x and y values range between. On my first graph, over the interval of 4 seconds, that's my parameter, the horizontal distance travels from 0 up to, looks like 160. So I can scale my horizontal axis, my x values, between 0 and 160. So let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it would be convenient just to scale this out by tens because that'll get me all the way up to 160, the final value. So halfway would be 80. And then each half of that would be 40. So then that would be 120. I'm not going to label all of them. I just want to get a sense of the scale. So that gives me an evenly scaled horizontal axis. And this is horizontal distance in feet. Then we're going to have the vertical distance, also in feet on the vertical axis. And to get a sense of how I want to scale that, I'm going to look at the range of values over the time interval for 4 seconds. So it looks like the minimum vertical distance is 0, which is reached at 4 seconds, and the maximum is 100, which is reached at 1.5 seconds. So I really, in terms of the horizontal scaling, I just need to scale between 0 and 100. So I know there's 16 boxes here because I've already counted them out on the other side. So I'm also just going to scale by 10 here. So I'll go 1, 2, 3, 4. So that'd be 40, 5, 6, 7, 8. That's 80, 7, 8, 9, 10. All right, sorry, 80, 90, 100. So up here would be 100. Here would be 60. And here would be 20. Okay, so I have each of those plots, and then I'm going to plot each of my points. So once I've scaled out my axes, I'll just go ahead and plug things in. So once I've used the parameter to find the x and y coordinates, I'm really done with it. And this is where this type of equation gets kind of interesting, because I'm really just plotting these two values on these axes. So I'm plotting 0, 64. So 0, 64 be about there. I'll label it so that you can see where it came from. 40, 96. So 40, 96 would be round about there. So when I get this final graph, t actually won't appear anywhere in it. That's why it's referred to as this parameter, because it's not a variable that I'm measuring anywhere in here. I have 80 and 96. 80 and 96 right here. And I'm just looking at these x and y values, 120, 64, 120, 64. And then 160, 0 down here. So I get a curve that looks, I'd imagine, something like this. Okay, which is what I expect for the path of an object being thrown in the air. If I throw any object, it typically follows a parabolic pathway. So I could see kind of the path that it has traveled. Okay, so that I got each of my values. So notice that this curve is really a combination of both of these curves together, but I can use those original two to get a sense of the scaling. So I'm really trying to take the relationship between these two variables and get them visually represented here, and I'm eliminating the parameter of time. Okay. In the next video, we are actually going to look at how to convert between parametric equations and rectangular equations so that we can kind of extend our knowledge of that set before we look at applying them to particular problems.